Alrighty, section 4.5, matrix inverses. Now, we have to be super careful when we talk about this chapter because we've already talked about one type of inverse with matrices. We talked about the additive inverse. Remember, that's where you add two matrices, or maybe matrices, pardon me, and you end up getting the zero matrix, right? You end up, all of the terms end up adding together to equal zero in every entry. This one is slightly different. Today we're going to be talking about the multiplicative inverse. It's the same kind of concept, right? But instead of receiving the zero matrix, we're going to get back the identity matrix after we multiply two things together. So it's the multiplicative identity. Just a little recall on what exactly the identity matrix is from a little while ago. Remember when we were solving systems with matrix, we ended up, we wanted this on the left-hand side, this matrix right here. It's called the identity. And we're going to soon today find out why it's being called the identity. Until then, we've kind of just been dealing with the fact that it was the identity. Today we're going to figure that out. So when you multiply something by an identity matrix, what you get back is exactly the same. So notice like here, we have this matrix, 5, 7, 2, 4, right? When you multiply it by the identity, all of the stuff remains the same. So you've got 5 times 1 plus 7 times 0, you still end up with 5. And in the same sense, you still end up with 7, you end up with 2, you end up with 4. In other words, the identity, when you multiply by it, doesn't change the matrix. It keeps it exactly the same. Hence, it's called the identity. It's pretty much the same idea as when you multiply 1 to any number. If you multiply 1 to 2, you get back 2. You multiply 1 to negative 2, you get back negative 2, right? So that's what the identity is. It's something that when you multiply it, you don't change anything. Now we've seen that it's much more powerful than just a 1, right? It can help us solve systems. It also can help us with the inverse of matrices, these multiplicative inverses. Identities come in every shape and size. All they need to have is a diagonal down sides. The sides, they only come in squares. But basically the idea is you've got a diagonal of 1s, everything else is 0. That's how you define an identity. When you multiply by the identity, so knowing that the identity is very much like 1, we can see what happens when we multiply this 3 by 3 by the identity. Instead of actually doing that, let's just use our logic skills. If I multiply A times an I3, an identity of 3 by 3 size, what would happen to A? Talk about it for a sec. What do you think? What would actually happen? What would I get back? That's right, I would just get back A, right? I would get the exact same matrix of negative 2, 4, 0, 3, 5, 9, and 0, 8, negative 6. The exact same matrix. Now, we're not going to do that today in class, but I recommend that you go home and try it yourself. You will definitely see, if you've done the multiplication correctly, that the identity will yield the exact same matrix. Much like when you multiply by 1, you end up with the same thing, right? Alright, finding the inverse of a matrix. When you want to find the inverse of a matrix, again, we're going to call it this fancy A with the negative 1. It just means A, it's not like to the negative 1 power or anything. It's just the inverse of the matrix, the multiplicative inverse. So a multiplicative inverse is very much like when you multiply 2 and 1/2, or in other words, when you multiply something like A times 1 over A. You're going to end up with 1, right? It's the same idea here. When you multiply a matrix and its multiplicative inverse, you get back to the identity. So, two matrices and they multiply together will give you the identity. If they are, in fact, inverses of each other. That's sort of the definition. So, an inverse gives you an identity. An inverse gives you an identity. So when you multiply two inverse together, you get back the identity. Now we can actually use that fact to solve for the inverse. If we want to find the inverse of a matrix, well, we know that a matrix times its inverse is supposed to equal the identity, right? So we can set up this sort of mini equation where we've got a matrix times some inverse, we don't know it yet, is equal to the identity. And from there, we can make sort of an augmented matrix. So we'll take it and we'll put it into an augmented matrix, and then we can solve that exactly like we did with row ops. So let's jump on down just a little bit to example 2.1, so we can see this with some real numbers that aren't spelled out for you. We're actually not going to do B because of time permitting. We're just going to use all this room for A, because we're actually going to go back and check this at the end too. So let's try this out. We've got this matrix here, negative 1, 2, 3, and 4. And we're going to multiply it by the identity. So in other words, we're going to set up a new matrix, set it over here, negative 1, negative 2, 3, and 4. And we're going to augment it, meaning we're going to stick that little line in between next to the identity. We're going to use an identity of the same size. So we're going to use a 2 by 2 identity matrix. All right. And now we're going to row up this guy. We're going to use our same elimination skills we've been using the entire chapter. And we're going to get the identity on the other side. So we're going to try and put the identity over here. Instead of having it on the right-hand side, we're going to get it on the left-hand side. Let's go ahead and start doing that. So first things first, I need this. So I'm shooting for a 1, 0, 0, 1 on the left-hand side. I need that first entry to be 1, right? I'm still going to go around in the same pattern. I'm still going to go around in the spiral. But I need that first guy to be a 1. Right now it's a negative 1. Quick, easy fix by just multiplying by a negative 1, right? So let's negative 1 times row 1 applied to row 1. We're going to keep row 2 exactly the same. Exactly the same. 3, 4, 0, 1. But the top row is going to be the negative version. So 1, 2, negative 1, and 0. Good. All right, so check on that first one. Check. Second, we need the 3 to become a 0. So let's pick a different color. We need that 3 to be a 0. So in order to get the 3 to be a 0, I'm going to do the same thing as if I was doing this with any other row operation. So I'm going to do negative 3 times row 1 plus row 2. And I'm going to apply that to row 2. So I have a new matrix. Right, new matrix. And I'm going to keep row 1 the same because all I'm changing is row 2. So 1, 2, negative 1, and 0. All right, so I'm going to keep the first row the same. But then I'm going to start multiplying this little guy into the second one. So negative 3 times row 1 is 1 times, so negative 3 times 1, it's going to be negative 3, plus 3 is going to give me a 0. That's the 0 I want. Negative 3 times 2 is going to be negative 6, plus 4 is going to give me negative 2. Negative 3 times negative 1, right? So each time I'm multiplying everything in row 1 by a negative 3, and I'm adding it to row 2, right? So negative 3 times negative 1 is 3, plus 0 is 3. And negative 3 times 0 is 0, plus 1 stays a 1. All right, and I got what I wanted. That 0 is a 0. Check. All right, moving right along. I now need the negative 2 to become a 1. So I'm going to multiply. Every time I need a 1, I just divide by what I have, right? So make it positive, negative. I'm going to have to multiply by a negative. 1/2 to row 2. So that gives me, row 2. And I'm only going to apply that to row 2. So again, row 1 stays the same. Actually, let's kind of zip up here. Kind of zip up there. And we'll draw this new one here. Row 1 is going to stay 1, 2, negative 1, and 0. But row 2 is going to stay 0, right? So 0 times 1/2 is negative 1/2 is 0. Negative 2 times negative 1/2 gives me the 1 I want. 3 times negative 1/2 is going to be negative 3/2. And 1 times negative 1/2 is going to be negative 1/2. Awesome. All right, and yes, we got some fractions, but again, all I'm shooting for right now is that this side becomes the identity, and I'm pretty dang close. So now I'm going to do the last one. I need that 2 to be a 0, right? I've done everything else. I just need that 2 to be a 0. In order for the 2 to become a 0, I have to add something to it. I need that other row to be a negative 2. So I'm going to multiply by negative 2 to row 2 and add it to row 1. And I'm going to apply that to row 1. So let's try this out. Row 2 is going to stay unaffected. So 0, 1, negative 3 halves. Whoops. Let's draw this just a little bit better. So I'll draw this a little tighter. So 0, 1, negative 3 halves, and negative 1 half, right? And then for the top, so I've got negative 2 times, negative 2 times 0 to 0 plus 1. It's going to give me a 1. Negative 2 times 1 plus 2 is going to be a 0. This one's a little bit more complicated. So negative 2 times that negative 3 halves, it's going to be a 6 on top, divided by 2 is going to be a 3. And then negative 2 times negative 1 half, that's going to be a positive 1, plus 0 is a 1. And I think I made a mistake. Oh, pardon me. So negative 3 times negative 3 halves times negative 2 would be 6 over 2, which is 3 minus 1. I forgot about the minus 1 there, pardon me. Would be a positive 2, not a positive 3. So that would be a positive 2. And we have our inverse. All right, so now we've got the identity on the left-hand side, right? We've got the identity over here, which means that this guy is our multiplicative inverse. Our multiplicative inverse is the matrix 2, 1, negative 3 halves, negative 1 half. Awesome. Let's double check that that is in fact the actual matrix. So let's multiply that by our first matrix. Multiply negative 1, negative 2, 3, and 4 times this other 2 by 2, 2, 1, negative 3 halves, negative 1 half. And hopefully we get our matrix of an identity, right? Hopefully if these two multiply together and they are in fact inverses, they should be the identity matrix. But let's double check that. So I'm going to do the first row by the first column. So this first row by the first column, and I'm actually going to do that in a different color so we can see it. So this first row by this first column, we get negative 1 times 2 plus negative 1 times negative 3 halves. I'm sorry, times negative 2 times negative 3 halves. And so we end up getting negative 2 plus, let's see, 6 over 2, which is negative 2 plus 3, or 1. So it looks like our first entry is going to be 1, which is good because that's what it's supposed to be, right? It's supposed to be the identity that starts with 1. Let's do the next row. So this row times that column this time. So we have negative 1 times 1. Come on, there we go. Plus negative 2 times negative 1 half. And we end up with negative 1 plus, well, 2 times 1 half is going to be a 1, right? And negative times negative is positive, so we end up with a 0, which is good because that's where we're supposed to end up. All right, second row. The second row times the first column here, that's 3 times 2 plus 4 times negative 3 halves. And that's equal to 6 plus, pardon me. 4 times negative 3 is negative 12 halves. Or 6 plus negative 6, which is 0. Sweet, got a 0 there. And then last but not least, let's do that last row. Let's do that last row by this last column. So that last row would be 3 times 1 plus 4 times negative 1 half, which would be, let's see, 3 times 1 is 3. And 4 times negative 1/2 would be negative 4/2. Or 3 plus negative 2, which is a 1. And look at that, our answer did yield the identity matrix. So it looks like these two were in fact inverses. So we solved via row ops for the matrix that would multiply together to get us the identity. Awesome, awesome. Alrighty, pause right now if you have any questions or concerns, comments. Otherwise, we're going to go on to something very, very, very similar. Alright, sometimes it doesn't work. Sometimes there is no inverse. Sometimes there is no matrix that multiplies together to get the identity. And it comes out of the same kind of logic where we didn't have a matrix or a solution to a system of equations, right? So remember, when we didn't have a solution, it meant that we had a parallel line set, or we had the line that was the same, right? And sometimes that happens here too. Sometimes you just have a multiple of each other, and sometimes it's not going to work. So let's pretend we don't know that. Let's pretend that this problem we think is going to work, and we want to find the inverse. So let's go ahead and set up a matrix. Okay, so we have 2, -4, 1, and -2. And we're going to augment that, meaning we're going to write that next to an identity. And we're going to try and solve it, right? So let's try and solve it. So I need that first row to be a 1. I think I'm just going to switch these two rows. So let's just switch these two rows. Remember, that's totally legal. I can totally switch those two rows. So I've got 1, -2, 0, 1, and 2, -4, 1, 0. So all I've done is switch the two rows. Now I've got that 1 there. Awesome. Alrighty, in order to get that 2 to a 0, I need to multiply this second one or the first one by -2 and add it to the second one. Just like if these were equations and I needed that 2 to be a 0. So and I'm going to apply that to row 2. When I do that, the row 1 stays the same, right? Row 1 is exactly the same. -2 times 1 is going to be -2. Plus 2 is 0. Sweet, I wanted that. -2 times -2 is going to be +4. Plus 4 is interesting. 0. 0 times -2 is going to be 1. Oh, sorry, 0 times -2 is going to be 0. And then I get a 1 there. And then I get a -2. And we have a problem. Remember, this was a problem last time. If your row completely goes to 0, then there is no way for that second value to be going back to a 1, right? So we're never going to get the identity matrix, and it looks like this was a carbon copy, right? So it looks like this first row was 2 times the second row, so they're actually the same row, right? So it didn't work, and there is no inverse. There's no inverse that is going to yield the identity matrix. That only happens sometimes, but it does happen. Alright, the last thing we're going to talk about today is using this to solve systems. Okay, so we've seen how this solves, we've seen how to solve a system this way. Sorry, we've seen basically how to solve a system this way, where we set up an augmented matrix and then we work through that, right? But there's a slightly different route that you can use as a fourth method for solving systems. So far, or sorry, a fifth one. There's graphing, there's substitution, there's elimination, there's solving via just a regular augmented matrix like you see on the page here. And then there's this last one where we solve using the inverse. Now using the inverse, we kind of have to set it up just the littlest bit differently. So let's take a look at this. Now in the past we've set up equations like this, with negative x plus y equals 1 and 2x minus y equals 1. We would set up an augmented matrix where we would just insert the coefficients. Cool, moving on, done. What we were really doing though was setting up a left-hand side matrix and a right-hand side matrix. So we can look at it just a little bit differently like this. And I don't think it's too far of a jump to see where this one comes from, right? So this left-hand side becomes its own matrix, and this right-hand side becomes its own matrix, right? So instead of one large 2 by 3 matrix, we've got a 2 by 2 and a 2 by 1, right? If we call the first side A, and we call the other side B, and then we make a matrix of our variables, x and y, and we call that x, big capital X, then we can see that A times x equals B, right? A times x equals B, which is awesome. Once we've done that, we can see that all we have to do in order to find out what x and y are, or in other words, to find out what x is move A to the other side. If this was just a regular equation, if this was just ax equals b, then I would just say divide by x, and you get x is equal to b over a, right? That's what it would be. If it was 2 and 3, you would just move a to the other side. With a matrix, remember our moving it to the other side, our dividing by a looks like an inverse. It looks like an inverse. So that's all we're going to do. We're going to take out a, we'll find its inverse, and we'll multiply it by b. We'll just move that a to the other side. Now remember, it's very important to remember that matrix multiplication is not commutative. So once you find a inverse, you cannot, I repeat, you cannot multiply b times a inverse. You do not want to multiply b times a inverse. You always want to multiply a inverse times b, okay? It's just the way this trick works. Alright, so let's try this out. Let's take this matrix. We're going to take this system, pardon me. We'll split it up into those matrices, and then we'll solve using this new method. So let's take this matrix, we're going to go over here. We're going to make it a matrix. First off, we're going to make it a matrix on one hand, times a variable equals another matrix. Okay, and you're going to help me figure out which exactly goes into what. So let's take a look. I want to make the left-hand side all the coefficients that are on the left-hand side. Okay, so that first matrix A, I want to make it the left-hand side coefficients. So let's take a look. The ones with the x's are 2 and 1, and negative 3 and 5. Alright, and those are being multiplied by x and y. X and y, right? Alright, pause here if you don't know where I got any of that. On the other hand, on the right-hand side, I can make a matrix of 4 and 2. Very similar to what we were doing last time, so just slightly different. This time we do have an x and y, but that's okay. Alright, that was our first step. Now what we need to do, so if we call this a, x, and b, we need to find the inverse of a. We need to find the inverse of that a. So let's go ahead and find the inverse of that a. So we've got the, let's do it down here. Alright, so the inverse of a is going to be 2, negative 3, 1, 5, that's a, right, times 1, 0, 0, 1. Now augmented with 1, 0, 0, 1. Then let's go ahead and solve that. We can start by switching. Let's give ourselves some room. I'm going to switch it. So I have 1, 5, 0, I'm sorry, not 0, 1, 0, and then 2, negative 3, 0, no, it was 0, 1, sorry, just kidding. 0, 1, and then 1, 0, right? So I switched the two rows so that 1 is at the top. Now I'm going to go up here. I'm trying to save some room later for when we multiply by b, so make sure you kind of section off the side here. But we can use some more space over here. Alright, then I'm going to take this 2, and it's going to become a 1, or it's become a 0. I'm going to multiply negative 2 times row 1 plus row 2. Alright, so row 1 is going to stay the same. So 1, 5, 0, 1. Now I've got negative 2 times 2 plus, or negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 5 is negative 10 plus negative 2 times 5. Yeah, negative 2 times 5 plus negative 3 is going to be negative 13. Over here, we've got negative 2 times 0 plus 1 is 1. And then last but not least, we have negative 2 times 1 plus 0 would be negative 2. Alright, from here, we're going to need to multiply by negative 1 over 13 to row 2, applied to row 2. And we end up with the same row 1. And then 0, 1, 1/13, and negative 2/13. Sorry, those signs should be switched because we multiplied by a negative. Alright, so 0, negative 1/13, and 2/13. And then last but not least, we need that to be a 0. So we're going to multiply by negative 5, row 1, plus row 2, take 2, row 1. So row 1 is going to stay the same. I'm sorry, row 2 is going to stay the same. And instead up at top we get 0 times negative 5 is 0, so that becomes just stays 1. That becomes 0. We end up getting 5/13 and 3/13. And we have our inverse. So this is A inverse. This guy right here is A inverse. Fabulous. Alright, so now we've got A inverse. Now what we need to do in order to solve this is take A inverse and multiply it by B. So let's go ahead and do that. We've got A inverse, which is 5 over 13, 3 over 13, negative 1 over 13, and 2 over 13. Multiply that by our 2 by 1, our B, our 4 by 2, our 4 and 2. Alright. Remember to pause at any time if you got lost or have any questions, right? But that's how you find A inverse, and now we're going to multiply it by B. When we do that, we end up getting, let's see, 5/13 times 4 would be 20/13, plus 3/13 times 13 is going to be 6/13, or 26/13, or 2. So we end up with a 2. Similarly, we have 4 times negative 13, so negative 4/13, plus 2 times 2/13 would be 4/13, or 0. Looks like we get 0. So it looks like that xy is equal to 2, 0, or in other words, our solution is going to be 2, 0. So even though we had to end up dealing with those 13ths, this was probably the fastest way to solve this problem. Even if we had gone the normal route, the one where we use the augmented matrix, we still would have ended up with those 13ths. We still would have ended up with fractions. This allowed us to do a very simple 2 by 2 times a 2 by 1 multiplication instead of having to do about 15 more row ops. So this is a good option sometimes when you can, feel that equation out, right? You can find that inverse, just multiply it by the other side and find your solution.